Hello everyone. Today I will be presenting my study, tibial bone strain in basketball players during dynamic tasks. Physical exercise brings numerous benefits to our body. Meanwhile, overtraining or exercise with improper form could increase the risk of sports-related injuries. One thing that not many people know is that even during walking or running, our shin bone is being bent due to the loads acting on it. For professional athletes who participate in sports with much higher intensity, such as track and field, basketball, their bones undergo greater load and might have less rest time due to frequent competition. It is like a wire being bent back and forth repetitively, and eventually it will cause failure. So can their bone always handle this repetitive loading without any problem? Not always. Therefore, the goal of our study is to investigate the load and strain distribution on the tibial bone during multiple basketball movements. In our study, we recruited 13 college-level basketball players to perform several common basketball movements, including sprinting, jumping, lateral shuffling, and etc. While performing activities, reflective markers were attached on their body so that the motion can be captured and analyzed with the force play data through computer software. And all the loads acting on the tibial bone during the stance phase of the activities can be extracted and further analyzed. Meanwhile, computer tomography scan of each subject's lower limbs were obtained. Finite element models of the tibial bone for each subject with their bone properties were built. There were two boundary conditions applied on the model. At the proximal end, the surface nodes were fixed in the space, and at the distal end, the model was fixed by springs with limited range of motion. Finally, during the simulation, the loads acting on the bone at each time frame during the stance phase were applied on the model. And we specifically aim at two 10mm thick sections at the middle and distal third part of the model for strain analysis. So far, we have analyzed 4 different movements, and here is an example of sprinting. The plot shows the medium tensile and compressive strength through the stance phase. The strain gradually reached its peak and then diminished as the stance phase ends. If we take a closer look at the middle section, we can see the strain distribution across the transverse plane during the stance phase and find out when and where does the peak strain occur in this particular region. As we compare the peak strains between 4 current activities among all the subjects, sprinting resulted in the greatest tension across the whole section. In the anterior quadrant alone, we found that jumping also yielded great tensile strain compared to other movements. For the compressive strain, sprinting generated the greatest strain across the whole section again, while jumping generated the greatest strain in the anterior quadrant. In general, the bone experienced greater compressive strength than the tensile in terms of magnitude. Overall, by comparing different activities, we found that the peak strain occur at a different time point with respect to different sports. And we can see from this plot of the medium strings as different activities have different shapes. Moreover, the peak tensile and compressive strain do not necessarily occur at the same time. Based on the strain failure criteria, most activities did not yield strain that close to the fracture limit. And currently, we divide the bone section into 4 anatomical regions as anterior, posterior, medial, and lateral. However, based on our collaborators' clinical experience, we're currently considering to analyze the strain in a more continuous fashion. On the other hand, we will also consider the effect of fatigue on the strain distribution and also individuals' kinematic patterns on the movements in the future. At the end, I would like to thank my lab members and my funding source for the support of this study. Thank you.